In this segment, I want to talk about what forces are and introduce the first of Newton's three laws of motion, which is cleverly called Newton's first law of motion. Okay, so first off, what is a force? The good news is you probably already have a nice intuitive understanding of what a force is. A force is simply a push or a pull. So a force is a push or a pull, and forces are measured in newtons. So the SI unit of force is a newton, and it is a compound unit. It's a kilogram meter per second squared. In the United States, in the English system, we use the pound. The pound is actually a unit of force, and it's analogous to the SI unit of a newton. And so how big is a newton? It turns out a newton is not that big of a force. A mnemonic I sometimes use is if we were in Europe, not in England, if we were in, Amsterdam, for example, and we ordered a quarter pounder, a quarter pound is about a newton. So we could call it a quarter pounder, but we could call it a Newton burger. So if you can remember that a Newton burger is a quarter pounder, then that's a good mnemonic to kind of help you remember how big a newton is. A newton is not a huge amount of force. It's about a quarter pound. So what else can we say about forces? A force is all about interactions, right? If there was only one object in the entire universe, then there would be no forces. Forces are interactions between objects. And so as we go through here, we're going to practice using some of this language. The object is the thing that the force is on. As we go through, I'll be calling this the object or the object of interest. So the object is the thing that the force is on. So in this case, this boxer's face is the object. This boxer is getting a force applied to his face, therefore the object is his face. Now, every force requires an agent. It's an interaction between two objects. There has to be the thing that the force is on, we call that the object, and there's the thing that is causing the force to happen, we call that the agent. So in this case, we see this football player throwing a ball, the object is the ball, the agent is the player's hand. In this case, I suppose the object is the boxer's face, the agent is the boxing glove. A force is a vector. Remember that a vector includes magnitude and direction, and so we could say that a force is a push or a pull in a certain direction. And so that's important. It's a vector. It requires a magnitude, which is measured in newtons, and a direction, which is like over there, right? Often in this class, if I ask you for a direction, I'm actually looking for some angle compared to what, usually the positive x-axis, but not always. Okay, lastly, and this is an interesting point here, forces can either be contact forces or long-range forces. What do I mean by that? Well, take, for example, this little wooden toy. This is one of my son's little wooden toys. Okay. What kind of forces can I apply? Well, I can push on it. Amazing. Okay, so what did I just do? I applied a force to this little wooden toy, causing it to move. But guess what? I had to push on the little wooden toy in order to move it, right? So I applied a contact force. That's what I mean by a contact force. But forces can be long range also. There's not as many long range forces in this world. Here's an example. Gravity, right? So gravity is an interaction between what two objects? This little wooden toy and the Earth in this case, right? So if the Earth wasn't there, there would be no gravity for this little wooden toy to interact with, right? So in this case, gravity is just pulling this object down. It's not like the Earth has to touch it, right? So that is a long-range force. It's a little weird. For right now, the only long-range force we're going to talk about is gravity. But there are others. Another long-range force, one of my favorite long-range forces, it's one of my 4 favorite long-range forces. There's only 4. Okay. Magnetism. Check it out. I've got this little metal alligator clip, and I've got these magnets here. And check it out. The magnets don't even have to touch the alligator clip to attract them. It is a long-range force. It's almost like magic, but it's not. It's science. Great. It's a little surprising. We're going to talk a little bit more about that as we go along. So forces can be contact forces or long-range forces. We've got this bat hitting the ball. That's a contact force. We've got gravity pulling on this coffee mug. That is a long-range force. Since force is a vector, we're going to draw it representing it with an arrow. How do we do that? We are going to represent the object as a particle. So we're in the particle model, so it's a dot. So whether it's a Buick, a piano, a amoeba, then we're just going to draw it as a dot. Whatever the object is, we draw it as a dot. And we represent the forces acting on that dot as a vector. And by convention, we always want to have our forces pointing away from the dot. Why do we do that? Well, it just keeps our drawings tidier. And when we go to make free body diagrams, which is something we're going to learn how to do later in this chapter, it keeps our free body diagrams well organized and helps us understand them. This is a convention, but it's one that is pretty universally done. And so what we mean by this, it's important to recognize that if we've got a force vector here, and it looks like this is not a force that extends over some distance, right? This is representing the force on an object at one location. That location is right here. And so this length is proportional to the magnitude of the force. It's not sort of indicating some spatial extent to the force. The force is happening right here. And this length should be proportional to the magnitude, or how many newtons it is. So we place the tail of the force vector on the particle, as I said. The force vector should be an arrow. It's in the direction that the force acts, and the length is proportional to the magnitude, or the size of the force. And we give it a label. In this case, we have cleverly named our force F. Great name. Okay, moving on. So what causes motion? What causes something to move? It's a question that's perplexed thinkers for a long, long time, right? What causes things to move? You know, Aristotle, who was sort of one of the first folks to think about this, he was a Greek, in 200 BC or something like that, he says, objects just want to come to rest, right? And if we have to, and if we want to get something moving, if we want to keep it moving, then we have to push on it. He didn't quite call it a force, but we have to push on it. And he distinguished between violent motion and natural motion. And violent motion was when you had to push on something to keep it moving, and natural motion was just stuff's at rest. But wait a minute. Is this at rest? I mean, it looks like it. At least in my camera, right? It looks like it's at rest. But wait a minute. Isn't the Earth spinning? Isn't the Earth spinning very quickly around its center? In fact, the Earth is rotating so fast that sitting here, I'm in Fort Collins right now, the surface of the Earth is moving like 700 miles an hour compared to the center of the Earth. So, is this at rest? No, it's not. It's moving super duper fast. Not only that, we're winging around the sun even faster than that. So this thing is actually just flying through space. Look at it. What's causing it to go that fast? Nothing. It just is. So what causes motion? You don't need to have a cause for motion. What changes motion is a force. So forces change motion, but nothing causes motion. And this is a direct contradiction to Aristotle, who thought that the natural state of things was to be at rest. And so, fast forward to Galileo in the 1600s, right? And we've already met Galileo in a previous lecture. But Galileo, he was one of the first people to really put an emphasis on experiment. And so he actually had these experiments with inclined planes, and he was rolling balls down them. It's all very interesting. But he came up with this sort of thought experiment. He didn't quite use this language. But he said, hey, what if we've got a child sliding on really smooth snow, and I give this child a big push. This child is going to slide for a while until they come to a stop, right? Okay. And the smoother the snow is, the farther they'll go. In fact, I could put this child on some super duper slick ice and give this child a push, and they'll slide even farther, but eventually they'll come to a stop. Why? Well, because of friction. Because of friction. And friction is a force. And so if we could imagine, and this is why it has to kind of be a thought experiment, if we could imagine a frictionless surface, which is just not really possible to create on Earth, really, a truly frictionless surface, but if we can imagine one in our mind where we can easily build a frictionless surface, then how far would this child slide before they came to rest? And the answer is forever. They would just keep on sliding forever, and they wouldn't come to rest because there's no friction. And so, what causes motion? Well, nothing causes motion. Forces cause changes in motion, but nothing causes motion. In other words, for something to be moving, it can just be moving. Like us, spinning around the center of the earth. We've just always been moving. When you slid out of the womb, you were moving at 700 miles per hour relative to the center of the earth. And you still are. It's not like someone's pushing on you. Newton's first law. Guess what? Newton didn't come up with this idea. Guess what? This is Galileo's idea. We call it Newton's first law because he was the first one to publish it with his second and third laws, and together they make a complete description of motion. And so he gets to call it Newton's first law, even though it was Galileo that first really had this idea. Consider an object with no force. If it is at rest, it will remain at rest, and if it is moving, it will continue to move in a straight line at a constant speed. You may have learned this before. Most people learn it in this form. An object in motion stays in motion, an object at rest stays at rest. And that's fine, as long as we remember, unless acted upon by an outside force. Okay, so if the total force on some object is 0, then it just keeps doing what it was doing. If it was at rest, it stays at rest. If it's moving, it will continue to move in a straight line at a constant speed. So that's Newton's first law. And again, it's contradictory to Aristotle's idea. And honestly, it is very surprising, even though most of us have encountered this at some point. I think most of us walk through the day with a basically Aristotelian view of motion. I'm going to try and convince you of that here in a little bit. So here is an application of Newton's first law. We see this is a car and a crash test dummy. And so we see here the car runs into the wall here. Okay, and what happens to the crash test dummy? This dummy just keeps moving, doesn't he? So here's a velocity vector for this crash test dummy. And this velocity vector doesn't change until down here, when the dummy runs into the steering wheel, right? And so we look at this and we say, well, why does the dummy keep moving? Is it because he's flung forward by the violent crash? No, it's not. It's because there's no force on him, right? At this point, the force is on the car. So what starts slowing down? The car. At this point, the force is still on the car. So what slows down? The car. There's no force on a crash test dummy to slow him down, so he keeps moving. At this point, there is a force on the dummy. It is from the steering wheel. And finally, the dummy starts to slow down. Let's do a real quick example. Okay, there's a lot of words here. That's all right. We'll take them one at a time. An elevator is being lifted up an elevator shaft at a constant speed by a steel cable as shown in the figure below. It's not below, it's to the right. I'm talking about this figure right here. All frictional effects, including air resistance, are negligible. Negligible means we don't need to account for them. So there's no friction and no air resistance. In this situation, the forces on the elevator are such that A, the upward force by the cable is greater than the downward force of gravity, or is the upward force of the cable equal to the downward force of gravity, or is the upward force of the cable smaller than the downward force of gravity, or none of the above. Why don't you pause the video, think about it, and I'll see you on the other side. Okay, well, let's see. There's some really important words up in here. Let's look at here. So it's being lifted at a constant speed, right? And we're neglecting all air resistance. So that means the only forces on there are just the cable pulling up and the weight pulling down. And I realize we haven't, we haven't really talked about identifying forces too much yet. So hopefully, usually students are okay with this. We got the cable that pulls up, and we've got the weight that pulls down. Okay, that's the only forces. And it's moving at a constant speed. So what does Newton's first law tell us? Well, Newton's first law tells us that if there's no forces acting on an object, then that object is moving in a straight line at a constant speed, or it is stopped. Now, we can flip that backwards. The logic works the other way, too. In other words, if something is moving in a straight line at a constant speed, or is just at rest, then the net force, or the total force acting on the object, is zero. So the logic goes in both ways. In this case, we have something that is moving at a constant speed. So what is the total force acting on it? It's zero, right? If the total force is equal to zero, then the force up must be exactly equal to the force down. Now, typically, when I give this question in class, I find that the vast majority of my class, maybe 75 to 80 to 90%, will choose A. And they'll choose A because I think because the elevator is moving up. There must be some force pulling it up if it's moving up. That's an Aristotelian mindset, right? That's the Aristotelian idea that if something's that there's some force required to keep something moving, and there's just not, right? So in this case, it requires balanced forces to keep something moving in a straight line at a constant speed. Well, in fact, that's always the case, right? It's always the case that if something is moving in a straight line at a constant speed, the total force is zero. Now, assuming that the elevator was at rest not that long ago, then we did have to have some net force to change its motion, right? So forces change something's motion. They're not required to sustain something's motion. So at some point in the very recent past, the force of the cable was greater than the gravity in order to get this elevator moving. But once it was moving at a constant speed in a straight line, the force from the cable is exactly equal to the force from gravity. Okay, here's another good example. This is an image of Voyager 1. And so Voyager 1 is the satellite, and it was launched in 1977, the same year I was launched. And it's currently moving at about 38,000 miles per hour away from Earth. I don't know, it's been about 5 years ago or something like that. NASA sent out a press release that Voyager had actually left our solar system. So it is now beyond the orbit of Neptune. It is the farthest away that any man-made object has ever been. It is outside of our solar system, just winging away from us at 38,000 miles an hour. Right now, it's something like 14 billion miles from Earth. I looked this up just before I started talking. And I had to change it, because this is pretty fast, and every semester, it's different, right? So what keeps it moving that fast? Well, nothing. Newton's first law. It got going that fast from some velocity that it was given when it was launched from the rocket that took it up into space. And then it did a couple of flybys of planets. You can do this thing called a gravitational assist, where it's basically a collision with a planet. If the planet's coming this way and your satellite's coming this way, it does this, and you can actually, under ideal circumstances, almost double the speed of your satellite by doing that. That's a topic for Chapter 8. At any rate, it got going real fast, I don't know, years and years ago, and it's still just going that fast. It's got a nuclear reactor on it, which is producing about half the power that it did when it was launched in 1977. It produces something like 50 watts, which, you know, a 50-watt light bulb just isn't that bright. So it's producing about 50 watts, which is enough power to, run the onboard computer and take some pictures and send those pictures back to the Earth. It's taking it's taking cosmic ray data and sending that back to the Earth. So the power it has is just to run the instruments. It doesn't have any jet in, right? You look at this picture, there's no jet engine, there's no nothing, right? There's no rocket. I guess it would have to be a rocket, not a jet engine in space. It doesn't have one, right? It's got some tiny little things to help it maintain stability, but it does not have any propulsion on it at all. So that's kind of crazy. Newton's first law, more surprising than it looks at first.